Thank you, everyone, for standing by, and welcome to our webinar entitled Investigating Hypoxia Dynamics in Lake Erie. This webinar series called Freshwater Science will highlight Ohio Sea Grant and partnering scientists every month. Every quarter is a different focus, from human health and fish farming to harmful algal blooms and human decision making, bringing applied research to the public on issues that affect our Lake Erie communities. I am Jill Gentis-Banicki from Ohio Sea Grant and Stone Laboratory, and joining me today is Fei Sung Yu Yuan, sorry, Dr. Yuan from Cleveland State University. Dr. Yuan is a professor at Cleveland State University. Over the past couple of decades, he has been working on several projects ranging from climate reconstructions in the southern Rocky Mountains to nutrient dynamics in Lake Erie, with the support from state and federal agencies such as Ohio Lake Erie Commission, Ohio Sea Grant, EPA, and the National Science Foundation. His primary research goal is to improve under the understanding of some key environmental processes for better anticipating future changes. We're delighted to have Dr. Yuan here today to discuss his research. But before we do that, just a few things about the logistics of the webinar. During our presentation, all participants will be in a listen-only mode. Afterwards, around 12:20, I will conduct a question and answer session. If you would like to ask a question during the presentation, please feel free to pull up that chat feature located at the bottom of your screen, and I will collect and pose your questions out to Dr. Yuan at the end of his presentation. As a reminder, this webinar has auto captioning and is being recorded to be posted onto our website for later viewing. Also, we will post a webinar survey in the chat feature toward the end of the half an hour. Please feel free to take a few minutes to fill out that survey. It always helps us continue to bring you great webinars. So without any further delay, I'd like to introduce Dr. Yuan presenting Investigating Hypoxia Dynamics in Lake Erie. And I think let me unmute you. I think you might be muted.
Oh,
Oh, sorry. I think I might have accidentally muted you when you unmuted yourself.
myself.
There you go.
Okay? Yeah. Okay. Good. Thank you, Jill, for the kind introduction. Yeah, I'm a professor here at the Cleveland State, and today, yeah, it's really a great opportunity to share some of the research I have been doing, working over the last couple of years. So, yes, so this kind of work have broad implication related to the science and the policymaker also, yeah, and yeah, normal people, that's care about the health of the lake area or other aquatic ecosystem. Okay, so today's talk will be focusing on a couple of questions. So the first question is, how special about Lake Erie hypoxia, right? What's the difference between this and other system? And the second one is we are talking about what's the mechanism behind. Okay, we are look at the cause. And the third question, we try to see some kind of the cause, right? And then the consequence, we look at the hypoxia have some kind of impact, environmental impact. Okay. So the last, we try to provide some kind of perspective, like long-term variability from our study of the sediment. Okay. So that's probably is the relative new part of the story. Okay. So before, I don't know. Okay, before I move, I want to take a moment to thank my student, Emilia, as a graduate student, just graduated this spring. Okay. Also, I want to thank several focus from the Northeast Ohio studios. They helped me a lot to get the mud from the lake. It's not easy business. Okay. Eric just Mark, yeah, also says, yeah, is that helping me. And also, I want to thank the Ohio, yeah, not Ohio, I mean, the US EPA, the Lake Guardian thing, okay, they have basically helped me, to get to the core easily, okay. Actually, I cannot, this lake is huge, take the sediment core is not easy business, okay. And lastly, obviously, Ohio Sea Grant funded this project. Without this funding, this is not possible. Okay. So now move on this. I want to share something, some kind of background. Okay, why we doing this, and what kind of question we are addressing. Okay. So the first thing, yeah, we'll look at the Lake Erie, right? Lake Erie, the hypoxia has been around for some time. Okay. And this we see some kind of impact, affect the fish habitat, like drinking water, affect the water for the people living in the Cleveland or other place, like, and also how to affect the water use, recreational water use. Okay. So that's we identified two problems: the algal bloom problem and the hypoxia problem. That's the leading environment problem, right? That's affect the delivery of the ecoservice. So yeah, so this has been around for some time. We also invest a lot of kind of efforts, like to try to contain the problem, like, and reduce the nutrient. But still, this things has been around. Okay. And so we are not totally understand why this is still be the issue. Okay. So that's the three questions we are talking about here is, basically we talk about 3C. Okay. One is the characteristics, another is the causes, right? Then the consequences. That's the main topic today. So we'll look at each individual question step by step. Okay. So the first we try to see what's special about this Lake Erie hypoxia, right? And yeah, we know that we have a lot of kind of study, okay, try to get a better understanding about the Lake Erie hypoxia. Okay. Second, I will using the isotopic data, carbon isotopic, try to get some insight, where the oxygen goes, right? And the oxygen is consumed mostly by the organic matter, like respiration or thing. Okay. So we try to give some kind of idea. Last we'll talk about the response, how this we know they have a lot of kind of chest metal deposit in the lake back to in 1950 or 60 or something. And this metal is not kind of, it's marble, some is marble, some is not, right? So they have some kind of response. We see, the manganese is coming out, right? The Cleveland Water Department always, reported this kind of events. But but this is just the one element. So how about the other elements, right? So they have some kind of response. So we can analyze the sediment matter concentration. So we could give some kind of idea about what's going on or how the long-term change in the hypoxia. Okay, so that's the basic kind of idea. So now we back to the first question, how where we are, where the study area, right? The Lake Erie is a huge, right? You have the three basin, Western Basin and the Central Basin, right? So the hypoxia mostly in the Central Basin. Okay, why is that? Because this is deep enough to have the stratification, but is shallow enough to have very thin hyperemia, right? That's the problem. In the Western Basin, we are not. It's not deep enough to have the stratified and water. I mean the stable, right? They have shorter living that the kind of stratification could have. But in the East Basin, the hyperemia is quite thick, right? So they tend not oxygen depletion is but it's not cause the hypoxia. Okay. Basically, it's not severe enough to have this kind of problem there. Okay. So that's the thing. So they have a lot of kind of activity going on. NOAA have 8 sites, like 4 in the nearshore sites, and 3 in the offshore there, 1 in the northern of nearshore. Right? Second, the US just they have a lot of kind efforts, the mooring sites, like basically monitoring the bottom water oxygen going. Then the US EPA is, they are doing the mostly focused on 10 in offshore index sites, like, and they studied back to 1983 or something, yeah. But they have the seabird CTD profile thing like going on every season. And the Ohio EPA also did a lot of work. Like they collected the seabird data, 4 transactions, like the Huron, the Rocky River, the Fairport, and the Geneva transactions. Okay. Also near the Cleveland area have some buoy, like, and they're by the I think Limonotech thing, like they are monitoring the water quality there. Okay. So I did a little study show that how this hypoxia look like, why it's different. Okay. And basically I look at the nearshore, offshore. Okay. And the left side is the temperature. The red represent the nearshore. The green one is a kind of offshore. Obviously the temperature is different. The nearshore is warmer, and the offshore is a little bit cooler. And the main feature is here, like the nearshore, show up the hypoxia earlier. This is talk about the probability, at this time, August, like you probably, the nearshore is mostly, you will probably see at least 50%. Okay, you will see the possibility the hypoxia. Okay, this is based on the 9-year data. Okay. And the offshore, mostly in the September, you will see the chances are fairly high. Okay, you got the so the question is why the nearshore, the the hypoxia occur earlier than the offshore, right? So they have a study by the USGS, the Richard people also know Mark, right? They have some kind of model. They did a lot of kind of modeling work. Okay, so they suggest this could be related to the bottom water at the vacuum, right? And also Mark suggests this is probably related to the downwelling. Okay, frequent persistent downwelling related to some kind of southwest wind, right? But they think that the thermocline is become thinner. That's the kind of maybe help form the nearshore hypoxia thing. Okay. And I looked at the Ohio EPA data collected last year, and this is the red one is the temperature, the blue one is the deal. Like in July mostly is near. This is the Rocky River transact from nearshore to offshore. It's quite quite the kind of hypoxic line nearshore. Offshore is it's have a lot of oxygen is about 8 or something. It's good, right? But in the September, this thing, nearshore is some area is hypoxic, some is not. Like I think the main feature is this. Okay, so that the playing out the what they say, the thermocline. Okay, the thermocline, we call the thermocline, right? The thermocline. So the thermocline in the July almost flat, right? A little bit, right? but in the September, it's kind of tilted, right? So that's probably is the main feature. Okay, should be, yeah. So this also in Fairport have similar kind of feature. Okay, in this July is kind of flat, right? But the neutral side is kind of mixing. Okay, and but the September also tilted. Okay, so this is also in the Geneva transact also have this kind of issue. Thing phenomenon. Okay, so I put everything together in the Rocky Rivers and the Fairport and the Geneva transact. Okay, in July is quite fair. Okay, this is basically is the thermocline position. Okay, the bottom is the lake beds, okay, lake floor or something. Okay, so in September, this is going on. So you see the hyperlinear line, and yeah, the volume of the hyperlinear or thickness of hyperlinear line at the beginning, this in the July is very small, right? And then go offshore is kind of thicker, right? So that's the thing, So yes, because the thermocline deepening, I think it's the biggest cost. Okay, it's not, yeah. So I basically proposed the kind of idea, this kind of model. I can nearshore offshore why this case, yeah. So the thermocline is deepening, yeah, cause the hyperlimnetic water demand, oxygen demand is kind of, we have warm water, right? The biological activity is much strong, right? And the thinning the thermocline, the thinning the hyperlinear line, so cause the effect of the SOD, sediment oxygen demand is more, sediment oxygen demand is more strong, right? Because you have less kind of volume or something. Okay, so that's the kind of mechanism. Okay. I also did a little bit of study based on the seabird data. Yeah, the US EPA have the seabird data, from 10 index station back to 1997. They started from 1993, but yeah, I don't know. Previous the early stage, some efforts probably is not quite useful. I don't know. Okay, but this show you some kind of data again, and over the last 20 years, something like a quarter century. Yeah, this they look like yeah. This is talk about DO, like the bottom DO in August, okay, and the dissolved oxygen, and yeah, I didn't see any kind of improvement, okay. And 2012, yeah, it's a kind of dip, right? It's a kind of worst case in some station, okay, but not everywhere. So that's the kind of instrument data here we have, okay. So the second topic we want to talk about using some kind of yeah, isotopic data, try to figure out what's going on there. Okay, we have a lot of kind of instrument or sensor-based data, but we don't have much information about the chemical reaction, biogeochemical reaction, right? The oxygen is consumed. They have some kind of impact, right? So we have the opportunity to be on the Lake Guardian collectors some surface water, bottom water, okay, and last year, yeah. So we have the help, yeah. So we basically look at the spring water. This is the summer bottom water delta OAT, oh, not delta, DO, dissolved oxygen, okay, dissolved oxygen, yeah. So when there is yeah, that's August 11, right? That's the middle of the August. And actually, we see two sides. Yeah, we saw two sides kind of hypoxia. The other is stress kind of high. Okay. Then the East Basin, that's the data is yeah, the number is about 8 9 or something like. But there's still some oxygen is consumed. Okay, this is no hypoxia happening there. Okay. So we took the sample, then do process sample, then do the send out for the delta C13, right? And this could give idea about the respiration process or something. Okay. So we see this is the split, the summer surface water and the summer bottom water. Okay. So in the surface water, the DIC concentration is going down, and the surface is the bottom is going up. Right? Why it going down? Because they have some kind of productivity going on. Right? Take the DIC out. And the bottom have a little bit, increase because the respiration going on, right? But in the eastern base, this is not significant, right? But the delta C13 data is more, more pronounced, to be honest, the effect. Okay, so in the surface water, this get more positive. There in the bottom water is more negative, right? Because the organic carbon is more negative. So the organic carbon become inorganic carbon. That's the affect the signal. Okay. So we are able to figure out how much oxygen, how much organic matter is respired, okay, based on a change from the initial from the spring value then to the summer hyperlinear value line. We know that the respiration value, okay, is about -25 something, okay. So we do a simple some kind of mixing model, okay, we are be able to figure out how much CO2 is produced, okay. So based on this chemical kind of reaction, we are able to know how much oxygen is consumed. Okay. So that's the kind of stable isotopic approach. From other perspective, the US EPA have the seabed data, right? So we are able to figure out how much oxygen is utilized, right? This is called the apparent oxygen utilization. So that's the thing, okay. So we come out to the result, this is basically most of the oxygen is consumed by this, kind of activity, okay. Because of the time limit, I cannot go too much detail here, okay. And basically it's 90% of the oxygen is consumed by the respiration, okay. So now we work on the last part is the response of the consequence, right? So we did some study back to a couple of years in the Western Basin, and we know some elements is much is marble, some is not. Okay, so we collected the surface sediment, right, using the Pontiac, and this uses some muscle inertial sample, but not a lot. Okay, and we it's about 10% or less sample have the muscle. Okay, most don't have any muscle. This is kind of normal sample. So we are using the surface sample, try to see how the sample actually responding the hypoxia, okay, the method. So we do the spring, like the summer, okay, and the nearshore, offshore, multiple sites. Okay, but this we cannot finish the whole thing because it's too late. The weather get bad, worse. We are got exhausted. Okay, so that's the results. Okay, results is we are talking about in the spring summer change. Okay, from all the elements. And we figured out the two elements is quite special. One is the copper, one the manganese. Manganese, that's the issue going on. But the copper is the most significant. Okay, so this lost in the sediment. Okay, so now we move on to work on this. Take a longer sediment core. Okay, so we try to figure out how the history change of the matter. Okay, so we took the piston core, took the box core. Actually, the box stuff first. Then this year we took the piston core. Okay, and this is the kind of size. Okay, the piston core results don't have time to show. Okay, to finish. So we have three called, offshore, nearshore, and somewhere in between. We have three called. We finished the analysis. Okay. So we try to see how this, the metal respond to the hypoxia. Okay. So that's the results, offshore results. Okay. The lead, zinc. Okay. So this is quite familiar to me. We did other places have a similar kind of signature. This is the peak in 1970 or 1960. Okay. And the copper is quite different. Okay. Usually it should be similar. Okay. And also we have something here in the in C2 core, you also have similar kind of lead zinc core data and the copper data is quite different. Okay. And the nearshore one, you also have a similar kind of curve, right? But the deposition rate is different. Look like it's much faster. Okay. Okay, so how to get the hypoxia signal from the metal, right? The idea is, we have the assumption the metal deposition, have the similar kind of ratio. Okay, that's the kind of, historically look at the metal, they have similar kind of ratio. So we try to remove the signal from the input loading difference, right? Sometimes you have the curve, right? So basically, the signal normalize the signal, remove the the anthropogenic that kind of signal. Okay, try to see that the leftover signal what to look like. That's the leftover signal. Okay, so yeah. So this is the offshore, that's the in between, that's the nearshore signal. Okay. So the interpretation is this, you have more positive value, it's more arctic, right? And because, this is, you have more negative value, you have more, less arctic, okay, or anaxic. The idea is, based on our initial study suggests that the copper is kind of leaching out in the reduced environment. So that's the thing. Okay. So now, we have this data, broadly, we can smooth data, get to see long-term curve, right? And I think this do make some sense, like earlier, it's more kind of arctic, okay? Then you have some kind of, in the 1940 or 1960, 70, this is kind of issue, like in the offshore thing, okay? But but they have some issue going on in the nearshore. Okay, later part of the nearshore, it's kind of look like getting better. This could be other issue going on, right? Maybe in Cleveland have more copper deposit in the lake. Also, I don't know have this kind of evidence or not. If not, this is mostly maybe they have some kind of improvement going on. Okay. But over the last 20 years, the signal is kind of mixed. Okay, look like it have some impact by the muscle or something. Okay, so the nearshore is kind of worse. Like it's more, it's a problem. And the offshore is also the problem, but somewhere in between is kind of improvement going on. Okay, so that's the kind of thing I generated. Okay. And obviously more work is needed. Okay, here is the kind of summary we have. And first, nearshore, offshore is kind of different, right? Second, we'll talk about what, why is that, right? Why the nearshore is, formed earlier, I think probably is related to the deepening of that thermocline thing, okay? And so this is we based on the oxygen delta OH, delta stable carbon isotope. We figured out that it's mostly by the organic matter respiration. Okay. And the fourth point is we see some matter is quite sensitive to the hypoxia. Okay, especially the copper look like the big kind of issue. Okay. And then we provide some kind of perspective from the matter. Okay, so I don't have time to talk more about this. Okay, so I should be stopped here. Okay, thank you for your time.
Yeah, thank you. Well, we have a few questions. We have actually had several that you have already answered in your
Okay.
presentation, so that was great. One of the questions we had was, if you could talk, they were wondering if Cleveland experiences many hypoxic events.
Okay. Cleveland, yeah. Cleveland is, we are near live in the near the southern coastline of this system. Yeah. So basically, we are affected by the nearshore hypoxia more closely. Yeah. So based on the data we have, okay. So probably I should show the data here. Yeah, basically we are talking about this data, right? And this is talk about the nearshore hypoxia, where they have some kind of nearshore hypoxia going on, the water could affect the intake water, right? To then pump into the system. So look at this thing, this is the duration is quite longer, right? The offshore probably, yeah, it's probably, yeah, 1 or 2 months thing, but this could be more than that. Okay. So the duration, but the nearshore is quite dynamic. Okay. So then could, yeah, probably not always, right? There, the probability compare the peak of this offshore is different. Okay. So the probability is relatively low. Compare that. It's also is depend on the weather condition. Okay.
Another question we had was if you wouldn't mind where you had the last summary conclusion slide, would you mind putting that one up again? And then the other question that we had was, what do you feel is the next step in your research?
Okay. Yeah, I think to be honest, this is kind of fascinating work area. For me, yeah, there are lots of kind of activity going on here. Many people are interested. Yeah, this is obviously a bigger kind of problem, a bigger kind of environment issue, right? People are wondering, this is the hypoxia is kind of a natural phenomena or not, right? Yeah, based on this metadata, we do see some kind of a long-term change, right? This thing is getting worse, right? And but we cut the nutrient, reduce the input of the phosphorus. Yeah, we see some kind of improvement, but the hypoxia is still there, right? So why is that? So the question is, could it be related, the response? Yeah, the organic material deposited in the lake, they take time to be, to be consumed or respired, right? So they have a lot of kind of area could be worked on. Yeah, I see, we still don't not quite well understand about this hypoxia dynamic. We have a lot of kind of sensor data recently collected by USGS, NOAA, EPA, right? And I would say, these areas, we probably have a more new development going on, yeah, in the future. Also, yeah, we did a little bit of the carbon isotope analysis. I think this is just, the beginning. Yeah, we know if you look at the USGS that in the bottom water profile thing, and they suggested the water, the oxygen, the hypolemia is not totally closed, and they have some kind of leakage going on. Okay, so they have something. Yeah, it's more than that happening. Okay, so that's another kind of area could be working on. So yeah. And also, yeah, I think we can measure the, basically the hypoxia is look at the something, near the sediment water interface, talk about oxygen consumed by the sediment, right? So they talk about the oxygen going to the sediment. So we don't have a lot of kind of measurement in the flux of the oxygen, right? How much oxygen is going to the sediment, how much CO2 is back to the water column, right? I don't see any kind of real measurement going on. Okay. And that's the kind of area. Also, people talk about how much the nutrient is built up, right, in the hyperemia. And I think they have some study. Of the Michigan University of Michigan people did some study about the phosphorus thing, right? But still, they how about the methane? How about the H2S, right? There's, they have also have kind of impact on the environment. So I think they have lot could be work on. Yeah, that's the kind of thing I can.
All right. Well, I think we have all the questions answered. So I will then just close up this webinar and let me do a little summary here. Thank you again so much, Dr. Yuan, for being willing to talk with us about your research. This was really an excellent discussion. I'd like to remind the participants that we have a survey URL for the webinar in the chat feature, so please feel free to take a few minutes to fill that out. This webinar series is sponsored by Ohio Sea Grant and will continue on in October with Ohio Sea Grant Extension's Nicole Wright, who will be talking about aquaculture. The registration link is in the chat. Thank you again, Dr. Yuan. We really appreciate you taking the time to talk about your research. We hope it was beneficial to everyone, and we hope that you'll join us again in an upcoming webinar. Thanks again, Dr. Yuan. This was really, really good. So we really appreciate it.
Thank you.
Thank you. Have a great afternoon.